In this video, we're going to learn how to use the nearest neighbor algorithm to approximate the cheapest Hamiltonian circuit. So take 3 deep breaths and let's make this math easy. All right, so in the brute force method video, we talked about how the brute force method is the only way that you can find the cheapest Hamiltonian circuit. However, the brute force method is very time consuming, and especially if you have large number of vertices, it may even be too overwhelming for a computer to calculate in a reasonable amount of time. And so because the brute force algorithm is so time consuming, we have some other algorithms that we use to help us calculate or find a cheaper Hamiltonian circuit. It may not necessarily be the cheapest, but will give us a good approximation that might work just as well. And so the first one that we're going to be looking at is the nearest neighbor algorithm. So the way the nearest neighbor algorithm works is you select a starting vertex. So for this traveling salesman, we're going to have him start at his home in Seattle. And you travel along the cheapest edge to an unvisited vertex. So essentially you're looking for the nearest neighbor. So to get to LA, it costs $70. To get to Chicago, it costs $145. To get to Atlanta, it costs $140, and to get to Dallas, it costs $120. And so if we look at all of those neighbors to Seattle, it looks like the nearest neighbor is LA. So he's going to go from Seattle to LA, which will cost $70. And then you look at all of the neighbors of LA, but you don't want to go back to a vertex that you've already visited, because a Hamiltonian circuit only visits each vertex once. So I'm going to look at this, and it looks like I've got 150, 100, and 170. And the cheapest one is 100, so I'm going to go from LA to Chicago. And then I look at all of the neighbors of Chicago that I haven't visited already. So that's just Dallas and Atlanta. And it looks like Atlanta is much cheaper. So I'll go to Atlanta. And then from Atlanta, I have to go to Dallas because that's the only vertex I haven't visited. And then to complete the circuit, I need to go back to Seattle. And so the cost of this Hamiltonian circuit is going to be 70 plus 100 plus 75 plus 85 plus 120. And so you'd figure out how much that costs, and that would be the Hamiltonian circuit that's approximated with the nearest neighbor algorithm. So in this example, it actually ends up giving you the cheapest circuit, but sometimes it won't necessarily be the cheapest one. So it really just depends on the graph of whether the approximation algorithm gives you the absolute cheapest or if it just gives you an approximately relatively cheap circuit, but it may not be the cheapest one. But in most cases, it's very helpful to use an algorithm like this compared to the brute force method, just because the brute force method takes so long. So let's do another example of this. So let's say that we were, redoing the problem that we did in the brute force method video, but we'll use the nearest neighbor algorithm instead. So if the grandmother wants to visit all of her grandkids in the other cities, and she starts in city A, the nearest neighbor is going to be city D, because the cost of going to city B is 4, D is 1, and C is 2. And so D is the nearest neighbor. And then from D, the nearest neighbor is C. And then from C, I can't go back to vertex A because I haven't visited vertex B yet. So I have to go to vertex B, which is quite expensive, and then I end up going back to A to complete my circuit. So the cost of this circuit, which is A, D, C, B, and A, that's going to equal 1 plus 8 plus 13 plus 4, which equals 26, I think. And in this case, this is not the cheapest circuit. And because this is such a small graph, it actually is the most expensive circuit, it turns out. But it is still approximately close, because the shortest circuit, or the cheapest circuit, is to go from A to B to D to C and then back to A. That one costs 23. And so that's the shortest one, and 23 is relatively close to 26. So even though it ended up giving us the most expensive circuit in the graph, it still is approximately close. So this is a good example of why the nearest neighbor algorithm is an approximation algorithm, and it doesn't necessarily always give you the cheapest circuit. And it's also important to notice that it matters which vertex you start on. So in this example, we started at vertex A because that's where the grandmother lived. However, if I start at vertex B, my nearest neighbor would be to A, and then to D, and then to C, and then to B, which is a different circuit. So why don't you guys try as an example to approximate the shortest Hamiltonian circuit with the nearest neighbor algorithm starting at vertex A, because it does matter which vertex you start at. So pause this video, practice this method, and then restart the video to see what my answer was. All right, so if we start at vertex A, the nearest neighbor to vertex A is vertex B, because $4 is the smallest number of the edges that are attached to vertex A. And then from there, vertex B, I could go to vertex E, because that would be the cheapest edge that leaves B. And then I could go to C, I think. That would be my next cheapest. And then I could go to D, and then I could go back up to A. And so this circuit would cost me $4 plus 6 plus 11 plus 7 plus 9. And when I add those up, that would give me 37, I think. So the approximately shortest Hamiltonian circuit would be 37 long. And I'm not sure on this one whether that actually is the shortest one. I think you have this question on your brute force assignment. So if you want to go back and look at that, you can see if that actually is the cheapest Hamiltonian circuit, but it is an approximation of the shortest Hamiltonian circuit. So that's the way that the nearest neighbor algorithm works. If you have any questions, let me know.